Hello, today we are going to go over the ferromagnetism and antiferromagnetism in magnetic materials. So before we looked at the creation at the diamagnetism and paramagnetism in magnetic materials, and we saw that the localized and delocalized magnetic moments are origin of this paramagnetism and diamagnetism. Now, in the case of ferromagnetism, we can look at the possible magnetic materials such as cobalt, nickel, and iron. So this, we know the best ferromagnetic materials, 3D materials, transition metals, and they can keep the ferromagnetic properties up to 1000 even to 1400 Kelvin. So in this case, when we will reach these temperatures, the magnetic moments will be disoriented because of the thermal interactions, and our ferromagnetic just turns into the simple metal. So this happens because of Zeeman energy exceeding kT. Zeeman energy taking smaller values than kT values, and these Zeeman energies we saw before, it is given by the interaction of magnetic moment and the magnetic field. So for example, in the case of cobalt, we can look at the, that it has 1400 Kelvin temperature, at which it loses ferromagnetic properties, and this corresponds to 120 millielectron volt. So if you equate the Zeeman energy, which is scalar multiplication of the magnetic moment of cobalt and the magnetic field inside of the ferromagnetic material, which is called also Weiss molecular field. So in this case, we can find out, we are taking into account that magnetic moment of cobalt is equal to 1.6 magneton volt, and we will find that this value of internal magnetic field, which is also Weiss magnetic molecular field, which equals to 1300 Tesla, which is very big value of the magnetic field. Now, if we take value of the radius of the cobalt atom equal to 0.25 nanometers, in this case we can find this current that's responsible for this very huge magnetic field, which is equal to 4 ampere. So both these values of magnetic field and the current are very large, and the origin of this magnetic field lies in the fact that we will have an ensemble of collection of magnetic moments, and they will be oriented in the same direction, and at the same time they will create magnetic field at each value of each side of the magnetic moment. And this magnetic field is called once again Weiss magnetic field. So if we look at this magnetic field from other side, for example, in the case of Heisenberg Hamiltonian, which we wrote, which as in this line. So this Hamiltonian we used before in explanation of diamagnetism and paramagnetism, but in the case of ferromagnetic material, we have to look at the other kind of Hamiltonian, which is now equal to this molecular field Hamiltonian is equal to this. So we have here that this Zeeman energy applied to each magnetic moment. In this case, we will have here this spin moment of the atom, and this will be just again some of these values here. So this is called using this mean field approximation. We can find that also that magnetic field created by this molecular field equals to this lambda times magnetization vector. M here is magnetization vector, and we can use this to find out here this average value of magnetization, which is equal to this here, where here Bj with argument equal to this expression here, Brillouin function. Now we know that for ferromagnetic materials there is so-called temperature as Curie temperature, and this Curie temperature is the temperature at which we will have vanishing magnetization. Now, using this brilliant temperature at the vanishing at the value of Tc equal to this, we can substitute again back to this equation here, and we find out here this lambda, and this lambda is called Weiss parameter. This Weiss parameter is actually this expression in expression here. This gives the magnetic field using the magnetization vector, and it's called Weiss parameter. Now, using these values of the Tc temperature, we can find this here Tc temperature, and if taken from the experimental experiments, we can find this lambda parameter for each material. Now, using this graph here, this graph shows this magnetization vector, and its standard brilliant function here. So different curves here correspond to the different values of the total moment J. So here is 1 over 2, here 3 over 2, and here is 7 over 2. So all these expressions, they have decay of the magnetization vector, which at Tc temperature equal to C will have value of magnetization equal to 0. And this Tc temperature is called Curie temperature. Now, at the small temperature, at around somewhere here, we will have approximation for the magnetization vector, which is equal to this line here, and this just shows the decay of the magnetic field. And at Tc value, we even can simplify this expression to this expression, and given this the square root of Tc minus T, and here at T value equal to C, this square root equal to 0, and subsequently this magnetization vector equal to 0. Now, if we look at the temperatures larger than Tc and apply here magnetic field, B magnetic field, this is now B magnetic field is external field, which adds to the molecular field here, and this gives a total magnetic field that's acting on this material. So here magnetization vector will be equal to this expression here, known from the electrodynamics, and we can find from here this kappa, which is called magnetic susceptibility, which equals to this expression here. So C here is a constant, and this law is called Curie-Weiss law. So in the paramagnetic case, we had kappa equal to C over T. Now we have here modification of this Curie law, and we have here in the denominator T minus Tc, and this is again Curie-Weiss temperature law. Now, if you look at the some other kind of magnetism, and it's not called ferromagnetism. So in the case of ferromagnetism, we will have two sublattices, and the one sublattice with magnetic moments directed upwards, and the second sublattice directed downwards, and we will have this. We will call the A and B sublattices. So in this material, we will have overall magnetization not equal to 0, because upper directed magnetic moment is larger in absolute value than down directed magnetic moments. And because of this, we will have here some value of magnetization here. So these materials possessing these properties are called ferrimagnets. And for this case, if you look at the magnetic fields, so here the magnetic field is in the sublattice given with this line here, and the magnetic field in the B sublattice is given with this line here, where lambda and mu are Weiss parameters for A and B sublattices. So using again mean field approximation, we can find here when we will have applied magnetic field. So here H is external magnetic field in this case, and we will have magnetization in A sublattice, which is equal to this line, and B sublattice will have magnetization equal to this line here. So because of the because of the magnetizations having different values opposed to each other, now we will have we have to subtract them. So for example, if we have Tc1 equal to Tc2, which is Curie temperature for each sublattice, we will have graph of magnetization vector versus T like this here. So here we have magnetization vector of A sublattice, and this is for B sublattice. So we take the difference of these magnetization vectors, and this gives us total magnetization versus temperature. So here we have second case. One we will have this lambda kappa, lambda much larger than mu. So base parameter for A sublattice is much larger than base parameter for B sublattice. And in this case, here we have two terms here. Each term corresponds to the magnetic susceptibility of this first term for A sublattice and this for B sublattice. So this is just a case of two sums of two susceptibilities. Now, in the case when mu larger than lambda, we will have this formula, a little bit complicated, and this is will be a case for the rare earth compounds and magnetic isolators. Now, if you look at antiferromagnetism, so this looks as before as ferromagnetism, but in this case, these A and B sublattices will have magnetic moments probably very close to each other. And magnetization vector here is very close to zero because they will nearly cancel each other. So this material is called antiferromagnetic. And for this case, we will have magnetization vectors for A sublattice and B sublattice corresponding to these lines here. And transition temperature in this case called nil temperature. And this nil temperature is found using this formula here. So this nil temperature is will be only transition temperature for antiferromagnetic materials. Now this is experiment that was done here for the two cases of applied magnetic field, and magnetic field here could be parallel to these spins. For example, upward direction of the magnetic field will be corresponding to the parallel direction of magnetic field, and it will be in the second case when it will be directly perpendicular to each other, to these spins. Now, in these two cases, we will have here magnetic susceptibility versus temperature looking like this, and here we will have parallel magnetic susceptibility, and this is perpendicular magnetic susceptibility. And for the temperature here, which is equal to about 67 Kelvin, for this material, which is marked as F2, and after transition temperature, it will just follow this paramagnetic behavior of the magnetic susceptibility. So in the case of the perpendicular, we can see that magnetic susceptibility doesn't change with temperature, whereas in the case of the parallel applied magnetic field, we will have here this magnetic susceptibility like this. So this is magnetic susceptibility for these two cases. So for this parallel case, and here we will have perpendicular case. So these look magnetic susceptibilities for two these cases. Thank you for your attention.